Okay, hello and welcome again. This is now week 3 of the post-Easter work for Reigate College Maths. This week we are looking at radians, which some of you may have met before in your physics course or other similar courses. Some of you may have never seen before. So, what we're going to look at today are what are radians, how are they defined, and what do we use them for? Effectively, what radians are another unit of measurement of angles. Up until now, you've pretty much only ever used degrees to measure an angle. Much like you can measure height in meters or in feet and inches, you can measure an angle in either degrees or in radians. Depending on what topic you're working on, some units will use degrees, some units will use radians, some units will use both. And we're going to look at a little bit this week which ones are which, but not go into tremendous detail until those specific topics come up, most likely next year. But let's first off look at how radians are defined. And where they come from is this. This is a sector. Hopefully, you all already know things about sectors. It's a section of a circle. So these straight lengths are the radii. We're going to call this angle here, well, this is the angle that we're interested in. We're going to call this angle theta. So, let's say this is the sector AOB. Angle theta equals 1 radian. The unit we use is, or the notation we use is rad for radian, if this arc length here if the arc length AB is also equal to R. So you can think of this as what happens if you have an equilateral sector. Okay, so all of the lengths are the same. This equals 1 radian. But how big is 1 radian? This is obviously not an accurate diagram, but let's put this idea into units that you have an appreciation of already. So, if this angle here is the angle subtended by this arc, so the length of this arc links to how big this angle is, which should make sense. The bigger the angle, the further round the circle this goes. So if we go all the way round, we have 360 degrees. For 360 degrees, that gives us a arc length of the whole circle. So if we have here our starting line and the whole circle, this is our arc length. The length is 2 pi r. This is 360 degrees. So let's think about how many radians we need to go all the way round. Well, it's clearly linked to this. So how much have we increased this by? To go all the way round, that's a better circle. our arc length has gone from r to 2 pi r, which means our angle has gone from 1 radian to 2 pi radians, which gives us the relationship that 2 pi radians is the same as 360 degrees. So pi radians is 180 degrees. So how much is 1 radian? Well, rearranging, we get 180 divided by pi, which is approximately to 1 decimal place, 57.3 degrees. So 1 radian is just a little less than 60 degrees. So how big is 1 degree? Well, it's pi over 180 radians, which is going to be a very small number. Okay, so 1 degree is 0.0175 radians. Very, very small. So we need to think about how to convert. Because this is very useful to be able to do. So if you have an angle in degrees and you want to convert it to radians, so let's say we have 15 degrees and we want that in radians. Well, we know that 1 degree is 180 over pi radians. Sorry, that's not. It's pi over 180. There we go. That makes more sense. This is a very small number. So to get 15, we do this times by 15. Okay, so we get that times by 15, which gives us pi over 12 radians. Typically, if you can, or unless you're told otherwise, you will always give your answer exact. Typically, it'll have pi in it, but not always. Pi is not the unit for radians. If we go the other way, it's very simple. We're going to times by 180 over pi. Same idea, but backwards. So if we've got pi over 12 radians, if we do pi over 12 times 180 over pi, that gives us 15 degrees, which is what we saw. This is sometimes useful. It's useful in terms of in the specification. It's useful for a few different topics that we'll get most of which we'll get onto this week. But why do we use degrees and radians at all? Why are there two different units that we use? There is a third, but it's not used ever anymore. It's been rarely used since the 18th century. Well, degrees are used a lot because when you're talking about large things, so let's say for instance we're talking about an aeroplane. It's travelling at a particular height, and hopefully you remember from GCSE, tends to travel on bearings. Now, because that's a big thing that we're talking about, an aeroplane is a large construct, we want to be able to talk about bearings in terms of large numbers. So, travelling on a bearing of 120 degrees means a lot more than if you gave the same unit in bearings. The same bearing in radians. Whereas radians, those numbers are very small, comparatively. Okay? We've seen that 360 degrees is the same size as 2 pi radians. 2 pi is around 6. So typically when we do a lot of algebra and calculus, we want to use small numbers so that everything is proportionally the right size. So when we start doing differentiation, integration, things like that, we need to use radians instead of degrees, otherwise our equations and formulae don't work. So, now we know how to convert between radians and degrees, and vice versa. If you turn to page 12 of your workbook, you should see questions 1 and 2 are effectively that, expressing various things in radians. Okay, so question 1, we've got 30 degrees, 60 degrees, 90 degrees, and 210 degrees. So if you take a moment now and pause the video, you can work out how many radians those are going to be. So 30 degrees you should have as pi over 6 radians. 60 degrees, pi over 3, and 90 degrees, pi over 2. 210 is a little bit more difficult. Now, very useful to think about is when converting in your head or getting an idea for size of number is compare this to 180. Is it bigger or smaller than 180, and how much bigger? So this is bigger than 180, which means our answer is going to be bigger than pi. The fraction that we get is going to be larger than 1. And in fact, the fraction we get is 7 over 6. So 210 degrees is 7 pi over 6 radians, which we may well often say as 7 pi by 6. Okay, so if you ever hear something by something else, that means division as well, like dy by dx. Here we've got 7 pi by 6. Question 2 is going the other way, expressing things in degrees that we've got in radians. It's 3 pi by 2. And then the last one is 6 pi. So let's think about this in a different way, not using a conversion factor. So remember, think about this in terms of a circle. Pi is half the way round the circle. Pi by 2 is a quarter of the way round. So pi by 4 is in there. It's exactly halfway between this axis and this axis. In degrees, halfway between 0 and 90 is 45. So 3 pi by 2, that's 3/4 of the way round our circle. So 3/4 of 360 is 270. 6 pi, well, all the way around once is 2 pi, then we go around again and around again. So this is the same as 3 times 360, which is 1080 degrees. So that's basic conversion of radians to degrees and degrees to radians. The next thing we need to look at is how we use our calculator. Because we're dealing with angles, it inevitably involves trigonometry, which is, the most important thing for radians. That's why a lot of the reason why we use them is with trigonometry. Now, this is very important as to how your calculator works. Whenever you type in a trig function and then a number, your calculator goes, okay, this angle, what unit is that in? Great, let's do trigonometry of that. Your calculator has to be told what unit it's in. It doesn't know that because you're putting 30 in here, you want to work in degrees. It doesn't do that. It doesn't go, oh, okay, well, I'm putting in 1. That's a very small number, so I know, because I've typed it, I'm probably working in radians. 1 radian we've seen is around 60 degrees. So we'd expect this answer to be around √3/2. It's not. Because your calculator goes, oh, look, this is 1 degree. Sine of 1 degree is a very, very small number. So when we are working in radians, you need to change your calculator. I'm going to show you quickly how to do that here, but there are pictures in your workbook page, so you can do that as well. So what you need to do is on any screen that you're working on, any of these, but typically you'll be using the Run Calculate option. You need to press Shift and then Setup. Hopefully you can all now see this menu, and then you see this option here for angle unit. You choose option 2, and then you get these options. Radian is what we need to change our calculator to. If you ever need to change it back to degree, then you can. This gradian, this is the nonsense unit of measuring angles that I mentioned before that we never, ever, ever use, so don't. So if we put it in radians, we now should see that sine 1 comes out as that. Now 1 radian is approximately 60 degrees. So let's put this back in degrees and let's see if we get the same thing. It's pretty close. Oops. Okay. It's not exact because it's not exactly the same, but it's pretty close. So going now to question 3 on page 13 of the workbook. just very quickly use your calculators, put them in radians mode, and then work out those 3 answers. So we've got sine of 0.1. Once you've changed your calculator into radians mode, you don't have to do anything special. You just type everything in as normal. Okay, sine of 0.1, 0.0998, cos pi over 2 is 0, which we should expect because of the cos graph, and then tan of 4. A little bit more than 1 there. So, using your calculator, converting between radians in degrees is very important. So, what I would like you to do is page 116, exercise 5A. This is just a case of practicing what we've done here, just getting used to using radians as a unit. Don't do the whole exercise, just do questions 1 to 5. Okay, this should not take long at all. Once you've done that, come back to the video and we'll look at, very briefly, exact trig ratios. So, much like in degrees, because radians, again, it's just a unit of measurement, we can work out exactly, or you can learn exact trig ratios. Angles that when you put them in to sine, cos, or tan, you get an exact number out. And likewise, if you do inverse sine, cos, or tan of those numbers, you get the exact angles back. Okay, so the main ones that you need to learn, or at least need to be aware of. Obviously, your calculators are very, very powerful and will do a lot of these for you. These are very useful to learn to recognize, not necessarily for solving trig equations, but for doing other things. Next year, we'll get onto something called the R alpha method, which is a very, very useful way to rearrange and solve trig relationships. Some of these questions, and also when we use the addition formulae, a lot of these questions can be done a lot quicker if you learn your trig ratios and you can spot things. It means you don't have to worry about working things out on your calculator, typing stuff in. You can save that time in the exam. So let's look at them. Hopefully, some of you will already know sine, cos, and tan of 30 degrees, 60 degrees, 45 degrees. Using the exact trig ratios in radians, the results are the same. The angle unit we use is different. So if we have pi over 6 sine, cos, and tan, pi over 3, and pi by 4. So, again, some of you may know these, some of you may not. Let's have a look at how to work them out. So for pi over 6 and pi over 3, what we do is we start with an equilateral triangle of side 2 and then cut it in half. Because it's equilateral, this angle is 60 degrees, because we've got our equilateral triangle here. or as equilateral as I can draw it. We're working in radians, so this is pi by 3 radians. This is half of that, so it's pi over 6. So sine is opposite over hypotenuse. So sine of pi over 6 is 1 over 2. Cos is adjacent over hypotenuse, root 3 over 2. Tan is opposite over adjacent, so 1 over root 3, which gives us root 3 over 3. You can check these on your calculators. So if we do sine of pi divided by 6, or pi over 6 if you prefer to use the fraction button, we get a half, which is what we got there. Pi over 3, we do the other way around. So sine of pi over 3, opposite over hypotenuse, root 3 over 2. Oh look, they're the same. Cos of pi over 3 is a half. Oh look, they're the same. That should happen. Tan of pi over 3 is root 3 over 1. Pi over 4, slightly different. We use a different triangle. We still use an isosceles right-angled triangle, but this time we have side length 1, so this is root 2, this is pi over 4. Sine, opposite over hypotenuse, 1 over root 2, which simplifies to root 2 over 2. Cos is the same. And then tan is 1. Now, why are these useful? They're useful for being able to work out the exact values if we know not acute angles. So if you turn to page 14 of your workbook, you can see this is question 1, filling in this table. So let's have a look at question 2. We're trying to work out the exact value of cos of 5 pi by 3 without using the calculator. So what we can do, there are lots of different ways to do this. And in reality, in the exam, just use your calculator. But if you can work these out using these, it can really help speed the process up. So what we do is we think, okay, we use what's known as the cast diagram, sometimes called the butterfly diagram. So what we do is we start at 0 and go anti-clockwise. So 5 pi over 3 puts us, so 5 pi over 3 is a little bit less than 2 pi. It's 1/3 less than 2 pi. So it's going to put us all the way around here. What we then do is we look at the acute angle created with the x-axis. If this angle here is 5 pi by 3, this angle here is going to be pi by 3. Which means that the size of cos of 5 pi by 3 is the same as the size of cos pi over 3. All we need to do now is figure out if it's positive or negative, and that's where the cast aspect comes in. So the letter tells us which trig ratios are positive in which of the 4 quadrants. So in this one, between 0 and pi over 2, all of the trig ratios are positive. Between pi over 2 and pi, sine is the only one that's positive. Here, tan, and here, cos. Our angle puts us in this quadrant here, which means cos is positive, so this is positive. We then go, okay, cos of pi over 3 is a half, so cos of 5 pi by 3 is a half. We can check it. And we can see our calculator confirms it. So all of them work this way. Positive angles go clockwise, negative angles go anti-clockwise. So let's look at question 2. Sine of minus 4 pi by 6. So let's just simplify that to start with. So we've got sine of minus 2 pi by 3. So again, let's think about that diagram. Where does 2 pi by 3 sit us? Well, 2/3 is bigger than a half and less than 1. It's minus, so we're going this way. So it puts us in here. We need to work out this angle. This angle is pi over 3. Because this one is 2 pi by 3. And half the way round is pi. So this is going to be the same size as sine pi over 3. We then need to work out, is it positive or negative? In this quadrant, tan is positive. It's the only one that is. So sine must be negative. So this is minus a half. Last one on this page is tan. So we've got tan of 10 pi by 3. So again, let's think about the diagram. It's a positive angle, so we're going clockwise, but 10 pi over 3, well, let's think about where that is. So 10 divided by 3 is 3.3 1/3. So we're going to go 1, 2, 3, and then 1/3. So that puts us down here. Again, what's this angle? Well, it's 1/3 because we've gone 3 halves. So this is the same as tan of pi by 3. Then, is it positive or negative? Tan is positive in this quadrant, so it's positive. Tan of pi by 3, we saw on the previous page, is, let's just look that one up again, tan of pi by 3 is √3. Now what I would say with this is really don't dwell on it too much. If you get it, phenomenal. That's great, and it really, really helps. If you don't, that's what your calculator's for. It tells us the answer. So we can very easily see that in the heat of an exam, if you're really stuck on this, use your calculator. Particularly those of you who are doing further maths, this is really useful to learn these, to get used to using these because of the complex number stuff that you are going to do in the second year. It uses this idea a lot of spinning around a point. How many rotations are you doing to give you what angles there are? Okay? I would like you to practice this a little bit, but not too much. So, what I would like you to do, please, is exercise 5B, which is page 118. Just do question 1. Okay, it's lots of parts, it's 9 parts, but just do question 1. The last thing we need to do is have a look at the graphs of trig functions in radians. So pause the video, do this question, and then come back. So, graphs of trig functions. So, we are using a different unit of measurement. Is that going to change the shape of the graph? No. All that it's going to do is change where we label our axes. Or not even where we label our axes, but what we're going to label our axes. So, looking on page 15 of your workbook, where you can see we've given you some pre-drawn graphs there. If you're doing this on paper, then you can sketch them as we go. So we've got this sine graph, which I'm going to draw, whoops, the best I can. That's not great. It'll do. So we've got y equals sine x. So what are we changing the unit of? Are we changing the unit of the y or the x? It's the x, because we're changing the unit of the angle, which is what goes inside our trig. This is what we're changing. We are not changing this. So whether you're working in degrees or radians, the units of the y-axis stay the same. So those dimensions stay the same. All that changes are these points. Sine of 90 degrees is 1. So in radians, pi over 2. Sine 180 is 0 in radians, pi. And so on. Going backwards, we can see there. And that's y equals sine x, drawn in radians. Cos and tan work in the same way. So cos, I'm just going to do from 0 to 2 pi. That'll do. Same idea. If you know the labels in degrees, you know the labels in radians. Because you just changed them. Tan. Now tan Obviously gets a little bit trickier because we've got the asymptotes. As I always say, draw those on first. Makes life a lot easier when you start to try and frame the graph and get it the right size. So, that's what the graph looks like. Again, we label. And we're done. Okay, so good work. That's everything for this video. What we will look at in the next video is going through how we can use the ideas of radians to solve problems involving circles. Thanks for watching.